Okay, everybody, we're gonna finish module 15 today. Last week, we stopped right here. We did example 15.2. So we're gonna continue from here. You may have had to do this. I have to look at my notes to see if I have already given you this experiment as what you need to do at home is coming up. But anyway, this is one of the experiments for 15.2. But we need to cover some more material. Figure 15.5 on page 499 gives you more information about circuits. You already know what a simple circuit looks like. Here's your battery. You have your resistors right there. And then all of a sudden, maybe I should start from current slide. Okay. And all of a sudden you have this thing. What is this thing? Well, this is a switch. This is how you represent a switch. And the switch can be open or it can be closed. You already know that a circuit needs to be closed to allow the flow of electrons that will allow whatever you have hooked in that circuit to work. Electrons need to move to provide the energy to do work. Okay. Anyway, it needs to be closed for it to do work for you. So if your switch is open, it's not working. Whatever you have hooked here, if those are lights, are not working. It needs to be closed for it to work. And you represent this with those lines right here. Okay, let's talk about open circuits. Here's an example of a closed circuit. So you had your battery is connected to this light bulb. Your wires go through the light bulb and then connect back to the battery. This is a closed circuit because there's no space between anything. Nothing is open like this. Okay, it's all connected. All of it is a continuous. Those electrons can move and do all that work for you. But in an open circuit, those electrons cannot move. Light bulb is off. So you need to know the definition for the open circuit. It says a circuit that does not have a complete connection. Open. It does not have a complete connection between the two sides of the battery, and then the flow does not work. There's no flow here. Okay, it stops right here. It may be coming out of your negative, those electrons, but they reach this space and it cannot continue. So it does not work for you. Okay, so know the definition and know what it means. It's not just a definition, but what does it mean? It means an open circuit, there's no flow of electrons, they're not working for you. Anything you have hooked to that circuit is not going to work if you have an open circuit. Okay, let's look at figures 15.6 and 15.7. I put them all together, pages 500. You can hook things in a series or in a parallel format. And what does that mean? It means you're going to have your batteries, you can have your filaments of whatever you have, your wires, usually copper. This is your switch right here. This represents a switch. So you can have it open or closed. It looks like it's closed right this minute. So there is a flow of electrons coming out of your negative side of the battery. And to put two resistors, one next to the other like this is resistors in a series circuit. This is called to be in a series. When you have them hooked this way, one on top of the other, meaning that the wires have different paths they can follow. The flow can go up to this one and then go back down this way. It can go up this way and then just go through this other wire and come back this way. Okay, this is called putting your resistors in a parallel circuit. Okay, so know the difference between a series circuit and a parallel circuit. And what happens is when you have a burnout light, to have them in a parallel circuit is better because it means that the flow is not caught. In a series format, when it reaches the burnout light, that burnout light is acting as an open switch. And you already know that if there is an open switch, the flow cannot continue. If you don't have a flow of electrons, this light right here cannot work either. Neither the one that's burned out, not the one that is still good, will work for you. You're not going to have any light. This is like an open circuit. But if you have them in parallel format, if you have your resistors, your light bulbs in a parallel format, it doesn't matter if one of them is burned out, because the flow can just follow a different path. This gets electrons and it's still closed. It follows this big loop right here. This is burnout. Okay? So you want to have them in parallel. It's better. You will be playing with this. In this lab, you're going to have to do that. You're going to have to show me a series and parallel resistors. So you're going to play with spoons and wires and light bulbs and all that stuff. It's going to be a lot of fun, actually. Let's keep talking about this. On page 504, figure 15.8, there's a lot of drawings here because you're going to have to draw stuff like this as well. And sometimes they're going to give you drawings and you're going to have to try to figure out what they're giving you and what they're asking. So you need to be able to read these drawings. You have resistors, so represented with the wiggly lines like this, up and down, but R stands for resistor. Okay? So you have 1, 2, 3 resistors. They're all in a series. You see these? They're connected in a series. You show me your current from the positive to the negative. That's how your current is flowing. When you have resistors in a series, you can add them up to find what's called the effective resistance. You could put just one resistor that would do the resistance of all three. So the resistance combined of all three is what you have there when you calculate the effective resistance, is all of them together. So here you have your definition. The effective resistor can substitute all the other ones because they act as one. And if you are in a series, you're going to add them up. As simple as that. Add them up. Whatever they give you in ohms for each one of them, add them up and you're going to have your effective resistance. And you're going to be doing that, okay? You will be doing that. Now, what about parallel? Resistors in a parallel format. You have your battery right here that provides your volts, your voltage right here. You already know that in a conventional current, you're going to be drawing your flow, your current this way. Here you go. But you know that electrons travel the other way. Anyway, here you have your resistors 1, 2, and 3. They are not in a series, they are parallel to one another. So you know that if one of them doesn't work, the other ones will continue to work. Okay? So let's see. You can if they ask you for the total current in here, you can break it down into sections. You could be calculating each one of the sections right here. Okay? I don't know why I put 1, 2, and 3, and then 2, 3, and 4. You should say 2, 3, and 4 here. So each one of them can be calculated separately because they are like separate circuits. But what you need to know is how to calculate the effective resistance when you have a parallel circuit. In the previous one, you just add them up. But when you have a parallel circuit, you find the effective resistance, which is the total resistance, this way. 1 divided by the total resistance or effective resistance is 1 divided by the resistance 1, resistance 2, resistance 3. As many resistors as you have, you will add the resistance for each one of the resistors there. That's a mouthful. Let me go back. So you will have to calculate each section of resistance. Okay. Sorry. There you go. Let's see how we put all of this together. Let's put this together. And it's not as complicated as it sounds because it's adding in fractions. It's not complicated. But the first example that makes you use this kind of knowledge is on page 506. It says, consider the circuit diagram below. So here you have your circuit, you have your series right here with resistors. They give you the resistance for each resistor. It says redraw the circuit with an effective resistor, so it's just one, that can replace the individual ones. Determine the resistance of this effective resistor. Let's do that. How do you do that? Okay, the first thing I need to do is find my mouse. Okay, let me go to the blackboard right here. So you draw a circuit. Start by drawing a circuit first, and it's asking you to draw just one resistor. So just put one wiggly in there. Okay, just put one wiggly. And let me see. I'm gonna make, I should have done, I'm sorry, let me do that in white. You're positive, you're negative, that's your battery. Connect them and put one resistor, because they're asking you to do that. They're asking you just to put one resistor. They want to know the effective resistance. I'm going to put total. I like total, but you can put an if you want, or effective. Just put the word effective right there. But it takes time to write stuff, so I like to do it this way. Now, you know that this kind of resistors were in a series. This was a series. I don't know what I call it before, but this is in a series. So because you have in a series, you can find the total by adding them up. Resistance 1 plus resistance 2 plus resistance 3. It doesn't matter how many resistors you have, you just add them up, and that will allow you to calculate the resistance effective. So do that. Just do it. Okay. Let me go back and find my numbers. I don't have them memorized. But what did they tell you? They said that one of them was 15. So your total or effective resistance is the 15 ohms plus 12 ohms. And that's going to be 27 ohms. So that means, I'm going to put in yellow, that after you do this, you're going to say that this resistance right here, this resistor effective has 27 ohms. This is what they're asking for, the circuit plus the resistance. And then you have solved this example. It's your turn. So on page 580, example number 1 is a similar kind of problem. I'm going to give you the answer. If you get it right, move on. If not, watch to see how it's done. So let me get to the board, get another page. I think I still have yellow, but if not, here we go. Your answer here is, that's number 1. Your answer is 0.66 amps. Okay. How did we solve this? If you didn't get this answer, watch to see how this is solved. I'm going to just draw what they're giving you here for a minute. I'm not going to draw it exactly the way they do it, because I like to put my battery here on this side. I just do. But they give you 3 resistors. Okay, I'm going to put one here, 1, 2, and 3. Okay, that's what they gave me. This is the circuit they gave me. One of them, the first one right here, resistor number 1, had a resistance of 5.2 ohms. The second one, resistor number 2, had a resistance of 10.3 ohms. And the last one, resistor number 3, had a resistance of 7.1 ohms. So that's what the problem gave me. Now, remember that this is in a series. Okay? So that's the first thing you need to notice, that this is in a series. They're asking me to calculate the flow, the current, using resistance. What? And the voltage. They give us the voltage too, didn't they? yeah, the voltage of the battery, I forgot to put it here, that was given to us to 1.5 volts. Okay. So the formula or equation that puts all of this together looks like this. Our current equals the voltage divided by the resistance. Well, this resistance is our total resistance for this circuit right here. We have a way to calculate the total resistance in a series. Remember that the total resistance in a series is just you adding them up. The effective resistance is resistance 1 plus resistance 2 plus however many resistors you have there in the resistance. So in this case, I'm going to just put it directly in the formula. My current is going to be my voltage divided by my resistance. I'm going to just put it directly in there. 1.5 volts, and then I'm just going to put all my resistance here added together. 5.2 plus 10.3 plus 7.1, and I put all of these in my calculator, and that's where I find that my current, my flow of current is 0.066 amps, which is the answer I gave you at the beginning. Okay, so you just need to put everything you have learned up to this point together to be able to solve this problem. Now let's go back to instructions. So here we go. We just did this. Let's move on. Second part of that example. Okay, second part of that example reads like this. It says, replace the two resistors in the circuit diagram below with an effective resistor. What is its resistance? Please notice that these resistors are in parallel, and you need to remember how to calculate resistance when you have parallel resistors in parallel circuits like that. How do we do that? Well, let me go back to the board right here, get a new page, and always start by writing down your formula. Yeah, not yellow, I want white. So it's 1 divided by the resistance total, which is your effective resistance, 1 resistance 1 plus 1 divided by resistance 2 plus 1 divided by resistance 3, and as many as resistors as you have there. You only have 2, so it's not going to be too bad. So 1 divided by our effective, I'm going to put effective here so you know it's an effective. But you see how long it takes to do that. That's why I put total, because it's the same kind of thing. It's going to be what? It's going to be 1 divided by 15 plus 1 divided by 12. They give us these numbers. 15 and 12 was given to us. So if you do this, this number is 0.151 divided by ohms, okay? Because the ohms were at the bottom. So is this what our answer needs to be? No, because that's 1 divided by the resistance effective. You need to calculate now. You need to put the effective at the top now. So our effective is 6.67 ohms, okay? Okay, and that is your answer, or it should be your answer. Do not end here. This is not the resistance effective. That's 1 divided by the resistance effective. So put this under the 1 here, 1 divided by this number, and you'll have the resistance effective. And that concludes that example. That example is done now. Okay, let's move on. Okay, let's look at figure 15.10 on page 508. It says a fuse in a circuit. You're familiar with fuses. All your houses have fuses to prevent things from burning down. If you have too much current, you can, remember what we talked about, this friction. Friction creates heat creates fire. So you put fuses. Fuses are this section right here represents a fuse. Is a thin strip of the conductor. So this wire right here is a little bit thinner, not a little, it can be a lot thinner. and is encased, usually by glass or something like that. Yeah, glass, this glass right here. But anyway, what happens if you have too much current? This little filament right here breaks. And if you break the circuit, remember, you have created now an open circuit. That means there's no more flow of electrons. It will not create a fire. Okay, this you see right here is the same as this right here. If you have a line through it, it means that this fuse is still working. You have a closed circuit unless the switch shows you that it's open. But this switch right here is closed. You see it's closed. Okay, so it's allowing the flow of electrons to go through. But if you see a fuse that looks like this, the box does not have a line connecting the two parts of the circuit. This is a broken circuit. It's a burn fuse. It's a burn fuse. There is no flow of electrons. It's acting as an open circuit. Okay? Okay. I hope it makes sense. If not, ask me questions. Let's look at example 15.4 on page 510. And remember that, let me see if I can move. I don't want to do that. I want to just move this down so I can read it. Maybe not. But if I move it all the way? Well, you have it in front of you so you can read it. But it says, an electrician is making a circuit that is diagrammed below. So they give you the diagram. She needs to decide how big a fuse to put on the circuit so that it can draw enough current to function, but not so much current that it will overheat. She has fuses rated 2, 4, and 6 amps. Which fuse should she use, and how much power will the circuits draw? Okay, lots of questions here going on. Lots and lots of questions. Let me find my notes so I'm not copying the numbers incorrectly, but here we go. New page. So we're doing example 15.4. That's what we're doing here, okay? Let me get my white. And we're doing example 15.4. Maybe I should draw it again. I'm hoping I don't have to draw it, but I'm going to draw it anyway. Here you go. I'm going to spend some time drawing, so you may want to forward it if you want to. Dun, dun, dun. And then here's another one, and here's another one, okay? And they want to know, here's a fuse. They want to know what kind of fuse they need to put right here, okay? And they give us the voltage, so 12 volts here. And for each one of these, they give us the resistance, 9.0 ohms. I'm putting them in different places so I don't get confused. 15 ohms. I don't have enough space to write it here, but you should put it as close as you can to it. 8.0 ohms. So this is the information they gave me, correct? So there are several questions going on here. They want to know what kind of fuse they need to put right here. What kind of fuse should she be putting here? To know what kind of fuse you need to put in this circuit, you need to know what kind of current they have, okay? So they want to know what current first. You need to find out what current is going on through here. So you know what kind of fuse will protect us from the current. So how do we calculate this current? Well, you know that the current equals our voltage divided by our total resistance, okay? So then we do have the voltage right here, and we have individual resistance. We don't have a total resistance. So our next step is to calculate the total resistance. So you needed to notice that this kind of circuit was in parallel formation, okay, parallel. And parallel means that if you want to find your resistance total or effective, you needed to use this formula. And so on, as many as you need. So 2 formulas now that you need to be using, okay? So we need to calculate this resistance using this formula up there. We don't have it. We do have the voltage. So let's get a different page and start calculating that resistance. How do we do that? Well, all three of them are in parallel. So we can directly put them in our formula. I'm sorry, I don't know what happened here. Let me get the pen. So I'm going to put the numbers in there. The resistance effective, just putting a T for total, equals 1 divided by 9.0 plus 1 divided by 15 was the other one. All these in ohms in the bottom part, and 1 divided by 8.0. If I do my math correctly, and you do it too, you should be getting 0.31 divided by ohms. You're not done yet, okay? Remember to divide 1 by 0.30 ohms to find your resistance total, and that is 3.3 ohms. Now I have what I need to calculate my current, because the voltage was given to me was 12 volts, and I just calculated that resistance, 3.3 ohms. If I put everything in my calculator, I get a current, electrical current, that is 3.6 amps. Okay, so let me put that dot there better. Okay, of the fuses that she had available, you had a 2, a 4, and a 6 amps fuse. Okay, of this right here, which one do I need to put in there to protect me from these if it gets higher than these? Okay, so let me get yellow. These right here would be the ideal fuse for us. 2 is too little, and 6 is too big. So 4 is all you need right there. Okay, that's what you need. Now, are we done? No. This was just one of the questions that they were asking us. The other question they were asking us was to find the electrical power. And again, I didn't change it to white. So what formula are we going to use? Remember that you have 2 formulas to use when you need to calculate electrical power, but only one of them has what you need. Okay, you have the current that you just found, and you also have the voltage. So use this equation, and you have everything. 3.6 amps multiplying 12 volts. And if you do your math correctly, you should get that the electrical power for this circuit was 43 watts. Okay? Yellow, yellow, yellow. And that's the second part of your answer is right here. Okay. Your turn. Extra practice problem number 5, page 580. I'm going to give you the answer. If you get the answer, move on. If not, check to see how it's done. So let me get my extra practice problems, and let me copy the answer so you know what this should look like. They wanted to know the current, and I'm trying to find it in my notes. Here it is. Okay, so for number 5, the answer for number 5, your current should be 0.22 amps. If you got this answer, you're done. I mean, you're done for right now. Keep moving on for the instruction. But if you didn't get this value, check to see how it is solved. So let's read the problem, okay? The first thing they always do is check to see what they're saying to you. It says, what is the current in the following circuit? And once again, I'm going to draw the circuit they give me. So I have my battery, and I have a circuit, and it's a complicated circuit because it goes like this. Okay, another one right here. I'm just drawing it right now, okay? Ting, ting, ting. And it is close. Okay. They gave me the voltage. So the battery right here provides 12.00 volts of electrical power, electrical potential. And there's a resistance 1 here, a resistance 2 here, and a resistance 3 right here in ohms given to me. Okay, that's given to me. This one is 54 ohms. This one right here is 54 ohms too. And this one right here is 28 ohms. Please notice that these two right here are in parallel, but whatever this becomes will be in a series with this one right here. And that's what you needed to notice, that this right here, okay, is in parallel. And you needed to solve this first to find a resistance total for this section of the circuit. And then you can add this to this one right here. That was the only tricky part in this problem. So let's do that. Let's find the resistance total or effective resistance for this section of our circuit. And let me get a new page. And let me get white. I don't know if I have a pen or not. I want white. So because this was parallel, you need to use this formula. Total, I put total, but it's effective, okay? Different books use different ways of doing that, naming it different things. Resistance 1, and you only have 2 of them, so I'm just going to put the 2 of them, but it would go on and on if you had more than 2. So you have the values for these. It's 1 divided by 54 ohms plus another one that is also 54 ohms. And the number you get here is 0.037, 1 divided by the ohm. We're not done yet. We actually need to find the resistance total, not 1 divided by the resistance total. And if you do the math, you're going to get a resistance of 27 ohms. Okay, let me go back to this right here. So this is 27 ohms. Okay, so you can substitute this section for this right here. And now it has become this kind of circuit. It has become, I'm not going to put it all right there, but it has become one resistor right here and the other resistor right here. So this now is in a series, and you know that you can add them up. You can add them up. So let's go to another page to be able to do that. So for the second part, your resistance is going to be an addition. Okay, your resistance is going to be your resistance 3 plus the effective resistance that you found a minute ago, which was 27 ohms. So you have 28 plus 27 ohms, and if you add them up, it gives you 55 ohms. Are we done? No, because that's not what they were asking. They were asking for the current, and that is your voltage divided by your resistance, this resistance that you just calculated. The voltage was given to you. The voltage was, I don't have it in front of me, but I'm going to have it in a minute. It's 12 volts. You found the resistance, 55 ohms. Do the math in your calculator, and your current, your flow of electrons is 0.22 amps. And that's your answer. That's where it came from. Okay, awesome. Let's go back to instruction. Okay. Another example for you. Okay, here's another example. So they're getting a tiny bit more complex for you. This is on page 512, and it looks like this. It says, determine the power drawn by the following circuit. They give you the battery's voltage, or the power. It could be a socket, okay? Then you have several resistors. Some are in parallel, some are in series. So that's going to be not a problem. You know how to solve each one of them, but you just have to take sections. You have to solve it by sections. And then you're going to have to do 6, 7, 8, and 9, which are more complex kind of examples. So now I'm going to get another page and we're going to solve that example so you know how to do this. And we're doing, let me get my pen. We're doing number 15 point, sorry, keep doing that, aren't I? Why? Doing example 15.5. Okay. I like to draw them so I have a mental image of what's going on. So I'm going to start by drawing it. I like to draw them this way. It doesn't matter, it's a circuit. So wait a minute. Am I doing the right one? Yeah. I'm a little tired. Let me drink some water. So maybe that will help. And I cannot stop the video because then it becomes 2 videos. And I don't want to do that. So let's draw these. You have kind of like this. And then what? It continues. It's kind of an ugly thing. It continues. It goes like this. Another one right here. And then this one that breaks right here. And this continues this way. And another one right here. And then another wire that connects the whole thing. Okay. So they give us the voltage is 1.5. 1.5 is our voltage. What else are they giving us? They're giving us each of the resistance. So we have a resistance 1 of 25 ohms. This one is resistance 2, we're going to call it, and that's going to be 15 ohms. The resistance right here, I don't know if I can put it in there, maybe put it right here, 11 ohms is going to be our resistance 3. Okay. And our last resistance 4 right here is going to be 35 ohms. If I'm copying this right, that's what your circuit looks like. And hopefully everybody has noticed that we have a mixture here of parallel and series. So what I want to do, if I was you, this is what I would do, is solve this right here and just create one resistance there. That makes sense to me. So we can have a circuit that looks like this, okay? I want a circuit that looks like this. The one right there, and then this becomes just one. Because this I can solve, okay? I want this to become this right here. So let's do that. Let's find the resistance total for this section right here. So R2 and R3 together. And these are in parallel. So you're going to calculate the resistance total for this section of your circuit by using this formula right here. However many you have. Let's do it. Let's do it. Let's calculate that resistance. So the effective resistance for that section of your circuit, it's going to be 1 divided by 15. You had the 15 plus 1 divided by 11. I'm copying it right. Those are the numbers that I have for that section of the circuit. So I'm going to already give you the total resistance for that section to be 6.33 ohms. Okay, so simplify the circuit so you know what you have. Okay, what do you have now? You have now simplified to look like this. Okay, you just calculated this. This resistance right here now is the 6.33 ohms. The other two were given to you. One is 25 and the other one is 35. So 25, I'm just going to put it 25 ohms and the 35 ohms that was given to you. But you simplified the circuit. Now you have them all in a series. Okay, so let's find the resistance in this circuit for the series that we have just created. And you know that you just have to add them. Just add them, the 25, the 6.33, and the 35 that was given to me. And if you add them up, the resistance now is 66 ohms. I just found the resistance for the whole circuit. Great. They wanted to know the power. I should have said why I'm doing this. I should have said that. But remember that to calculate the power, you could use this equation or formula, but you also could use see which one did I use. Yeah, I used this one. I calculated my electrical potential with the other one. And for this one, I needed my resistance. So I just calculated my resistance that I needed here. Okay. So I can calculate my current by modifying this. Voltage was given to me, and now my resistance that I just calculated this resistance will be going right here. So let's put the numbers in. Voltage was given to you. This is given to you. So copy it. 1.5. I thought that was just the eraser, but no, it's the whole thing. So let's try this again. Let's try this again for a second. So I'm trying to calculate my power. Power equals my current times my voltage. Voltage is given to me. I need my current. I have my current can be calculated by using this equation. Voltage divided by resistance. Okay, that's where we were. So voltage is given to me. My voltage is 1.5. And my resistance I calculated by simplifying the circuit. And we found that our resistance was 66 ohms. So I have all the numbers I need. Okay, so if you do that, you find that your current is 0.023 amps. Okay, amps. Now, we're not done because that's not what they were asking. They were asking for the power, the electrical power, but we were missing this. That's why we had to calculate that. Put it in the formula for power. Put that 0.033. But let me see. I'm telling you, I'm getting tired here, but we'll finish soon. So this is 23 amps, and you're multiplying that. You're dividing that. You're dividing that by. I'm multiplying that. What am I doing? I'm doing this right here. This is what I'm doing. Come on, Miss Monica, pay attention. You're multiplying by the voltage that was given to you. So 1.5 volts. Okay? Put everything in your calculator. So if you put everything in your calculator, your electric power produced in this circuit is 0.035 watts. Okay. And that's your answer. Okay, that is your answer. There you go. Now we finish this one. Great. I hope it makes sense. Now, extra practice problem number 6. And as I said before, that was the last example. So these are more for you to practice because it's just breaking down the circuits, making a circuit that's more simple to use when you're trying to calculate what they're asking you to calculate. So it's all about that. breaking down those series and parallels and all that stuff. So let's do number 6. Let's do number 6 very quickly. Let me put the answer, and if you have the answer, then you don't need to watch how this is done. But they were asking for the current. So number 6, the current is 0.42 amps. And if you got that, you're done for number 6. Just move on to number 7. But if you didn't, let's talk about this one. Wow, that's an interesting one. So I'm gonna try to copy it first so we can break it down. Let's see. I'm gonna just copy the drawing. Bear with me. Here's one. And here we have another one. Another resistor and another resistor. And then finally, all of this is connected. And here's your source of voltage. There you go. Okay. So this is what it looks like, okay? This is what it looks like. I'm gonna name this resistance 1, and you have the numbers in your page, and I don't have a lot of room to put them here, so I'm just gonna call them resistance 1, 2, 3, and 4. Okay. And the voltage is given to you 6.0 volts. So this is what they give you. And it looks kind of scary, doesn't it? But you need to realize that you have areas. This right here can be combined to have a total resistance for this area. And then you can also find the total resistance for this area to simplify this circuit. Because what you want to do is come up with a circuit that looks like this. A much simpler circuit that looks like this. Okay. This one here becomes this one here, and this one becomes this one here. So you're trying to simplify the more complex circuit into something that's a lot more simple. And you know how to do that, okay? Let's start with this area right here. I'm going to call it area 1. Area 1. And I'm going to call this area 2. So I don't get confused. And we're going to start with area 1. Let's solve the resistance for this area. Okay, for area 1, let's find out what that is. Let me get all my numbers. Because those are in parallel, to find the resistance effective, you already know that you need to use this formula. Okay, 1, R1. I don't know what numbers you have there, but for the R's, R2, that's the formula that they give you. As many as you have in that area, okay? So if I look at my area 1, what I notice is that the numbers they give me are these ones. 1 divided by 18 ohms plus 1 divided by 11 ohms. So I find this number. If I put everything in my calculator, I get 1 divided by ohms. I'm not done. To find my total for area 1, just for area 1, I need to do 1 divided by this number, and I find that my resistance for that area is 6.85 ohms. So let's go back and say that the area 1 resistance is 6.85. I'm copying this right, okay? Very good. So now we're going to try to find resistance for the area number 2. So let's find the total resistance for this area right here. Let me get another page. And once again, it's the same formula we used before because it's still in parallel, but it looks like this. For area 2, total is going to be 1 divided by 13 ohms plus 1 divided by 17 ohms. And if you do the math, you get 0.136. 1 divided by ohms, and then you still need to find that total for area 2 equals 7.65, not 65. Getting smarter about my erasers. There you go. 7.35 ohms. Okay? So now I have found the resistance for that area. Let me go back and put it right here. 7.35. I can solve this. This now has become a series and I can add them up. Okay? So let's do that. Let's do that. The question here was the current. They wanted to know the current. The current is your voltage divided by your resistance for that circuit. So we are trying to find this resistance. Let's do that. Resistance total here is going to be the resistance in area 1 plus my resistance in area 2. I hope everybody sees that because it has become a series of resistors. And I just need to add them up. So 6 point, did we say 85? Yeah, 85 plus 7.35 ohms. If you add them up, they give you a resistance of 14.20 ohms. Now I have everything I need to put in this equation. The volts were given to you, 6.0 volts voltage, and the resistance you calculated 14.20 ohms. Do the math, and you should find a current of 0.42 amps. And that was your answer. All done with this one. Let's move on to number 7. Extra practice number 7. Let me give you the answer. And remember, if you get it right, just move on. They were asking for the power, I think. Wasn't it the power? Let me see. What is the power drawn by the following circuit? So yeah, they're asking for the power. And according to my notes, your answer should be, why is this has stopped working? Okay, here we go. 1,100 volts. Yep, that's what I found. So what? Power, what formula are we going to use? Power, I'm trying to find the circuit first. Let me find, I'm going to draw it. I always draw it. I'm going to copy just the way it is in here. We have this right here. Another one right here, another resistor. And another resistor right here. And the battery is right here. Okay. And another resistor right here. Okay. So this is what it looks like. Number 7 looks like this. So I hope you all have noticed that this area right here, you're going to have to solve first. You're going to have to solve this to simplify this circuit. Okay. Because if you want to calculate the power, the formula for the power, do I have a pencil in white? Okay. To calculate the power equals your current times your voltage. We don't have this. We need to find our current. But we can find our current by using the formula of current equals voltage divided by your resistance. We need just one resistance. So the resistance for the whole circuit. The first thing we need to do is find out what kind of resistance we have here. So we can simplify these into this kind of circuit. Ting, 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 and ting, 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 and your battery. Okay. So you're trying to put them all in a series. Get rid of the parallel every single time. Always get rid of the parallel first. How do we do that? Okay, I didn't put the numbers there because you have the picture in front of you, okay? But here you go. For that area, the area where you have your parallel resistors, you need to find it with this formula. As many resistors as you have, okay? Thankfully, we only have the 2. So 1 divided by the effective resistance for that area is 1 divided by 520, those are pretty big numbers, ohms, plus 1 divided by 480 ohms. And if you do the math, that comes out to 0.0041 divided by ohms. Not done yet. Your effective resistance equals 1 divided by this number, which makes it 250 ohms. Let's go back with this one. Yeah. So we just found that the resistance in this area, okay, is 250 ohms. Now you have a simple circuit, and you can find the resistance by adding them all up. Let's do that. Let's find the resistance total for the whole circuit. So your resistance effective for that. And remember that sometimes I say effective, sometimes I say total, just because I want you to notice that it's the same thing. I want you to notice that. And it's a 250 ohms plus 210 ohms plus 230 ohms. Add them up, and you should find that the resistance total for this circuit is 690 ohms. Now I have everything I need to find my current. My current is the voltage that was given to us. So what is that? 880 volts divided by this number I just found, 690 ohms. And if you do the math, you come up with a current of 1.3 amps. We're not done because they didn't ask for the current. They asked us for the power, the electrical power in this circuit. But we know that if we use this formula and we have everything we need for this formula, we can calculate that power. We just calculated the current. That's the 1.3 amps. And the voltage was given to us. The voltage is in your problem. So that's 880 amps. No, not amps, volts. Dun, dun, dun. Up. Volts. Okay. And if you do the math, then you find that number I mentioned at the beginning of our problem. I'm trying to find it again. I lost it for some reason. But I'm trying to cut, I think I put volts before, it should say watts. 1,100 watts, okay? It's watts. Okay, power is in watts. Sorry about that. I should say watts. Okay, there you go. It's in watts. Okay. Now we're doing number 8. So we are slowly but surely moving along. The problems are getting a tiny bit more difficult. Just the drawings look scary, but if you can break things down, they simplify into something more manageable. So number 8, if you did not look at number 7, I made a mistake when I gave you the value for the units of your power. That should have been in watts. So it was 1,100 watts, okay? Watts. to tease. Just in case you are skipping to number 8. It's not bolts. I don't know why I put bolts, but it was what. But here we go. Number 8. Let me draw number 8. Actually, let me give you the value first. Pen. Let me get yellow. And the value for number 8, the question was, what was the question for number 8? What is the power drawn by the following circuit? So once again, is your power. They're asking for power in watts again. And the answer is 1.8 watts. So 1.8 watts. Okay. If you got that, you're done. If you didn't get this, check to see how this was done. I like to draw first what they're giving me so I can make areas. Ooh, that looks interesting. You have a big long line like this. Then you have a resistor right here. Have a big long line like this. And then you have a resistor here in the middle. And they put the battery or the socket or whatever here in the middle. Okay, that's where they put it. And here's another resistor. And then here's another resistor. And finally is one more resistor. There's one more resistor here at the end. Okay. Very good. All right. So hopefully you can simplify this. See that this is an area. Here's another area of parallel circuits. And we need to kind of simplify. Let's start by simplifying those areas. And then what does it become? Let's try that first. If we do that, what would it look like? We did that, we would have something that looked like this. One resistance right here, and then a battery right here, and then one resistor right here, correct? Okay, maybe I should make it nicer. Okay, let's try this again. Okay, it would look like, here is my resistor, something like this. Is that gonna be helpful? Let's think about this for a second. Maybe. Maybe it will be helpful, maybe not. Let's see, what else could I have done? These 3 are 1, but this is still in a kind of a series. So maybe I can put them just all in a series. Could I put them all in a series? There's 1, 2, 3, 4, 5. 5 of them. And if I just draw it like this, they're still in a parallel format. They're still in a parallel format. That is not going to help me. 1, 2, 3, 1, 2, 3, 4, 5. So what I'm going to do, I mean, you could do these, you could break them down into the 2 different ones, but then you would still have to notice they're still in a parallel format. They're still in a parallel format. I would still have to add them as parallel resistors. So I can go ahead and add the whole thing, all of it, as parallel circuits. Okay, all of them. I can do that. So let me get another page, because once I draw that picture, I saw that they were still in parallel, and I would have to add them as parallel. So I might as well just put them all together from the beginning. Okay. They're asking for the power. And once again, remember that your power comes from this formula. Your current times your voltage. You do have your voltage, but you need to find your current. You need to find your current, and you find your current with this other formula That's why we need to find the total resistance of that circuit. And I said to you, once you try to simplify it, it looked like you still needed to simplify it some more, so you could add them all up as parallel circuits. So I'm going to go directly and do that because you already know how to do that. Total one is add them all up as parallel circuits. 5.0 ohms plus 1 divided by 15 ohms plus 1 divided by 4.0 ohms plus 1 divided by 5.0 ohms plus 1 divided by 20 ohms. So put all of these in your calculator. Just put it there in the calculator. And if you do that, you should be getting a value of 0.771 divided by ohms. So your resistance total equals 1 divided by this number, 0.77, which is 1.3 ohms. You just found this R right here, the total resistance for that circuit. That allows us to calculate the current. So let's put it in the formula for the current because we did have the voltage. The voltage was given to us. So the voltage was 1.5 volts and the resistance you just found 1.3 ohms. Put it in your calculator and you find your current to be 1.2 amps. Not done yet, okay? Next step is find your power, and you know that the power was the current times your voltage, and you have everything. 1.2 amps multiplying 1.5, and remember that your units are watts, so 1.8. Okay, now we are talking. Remember that draw things. Let me see if I can go back. Maybe one more. Draw things, notice things. Like when I drew these, it was like, okay, I'm still in a parallel format. That's not going to help me very much. I'm going to have to add them anyway as a parallel format. So let's add them all together. So make connections like this. Draw, draw, and draw. Okay, number 9. Number 9. Let me give you the value for number 9. So number 9, I'm looking for my answers right here. Number 9, it looks like your fuse needed to be 10 amps fuse, okay? If you found this number, you are done. And if you didn't find this number, check to see how this was done. Let me look at the picture. Okay, it says, if an electrician has 1, 5, and 10 amps, which should be used to protect this circuit? So let me draw the circuit right here and see what we have. So your circuit looks like this. And they put the fuse right here. This should be connected, remember? If it's not connected, it's not working. I don't know why they didn't put a line in there, but that's okay. Here you go. Maybe it's waiting for you to put something in there. And here you go, another resistance right here, the resistor, and the last one right here. Okay. My pictures are not very pretty, but that's what I see. Now, let's try to simplify this. If I put all of this together, will it simplify my circuit? Let's draw it again with this area simplified. So now all of this has become just one resistor. It has become one resistor, and my fuse will be going here. This now has become resistors in a series. So that's simplified. It will work. If I do this, it will work. So I need to calculate the resistance in this area. Okay, I need to calculate the resistance in this area. All of these are in parallel, and you know that to calculate the total resistance when you have parallel stuff, you use this formula. So use it, okay, as many as you have. So let me get my numbers, because I have not memorized my numbers, and I'm not going to be using the calculator. I just copied my numbers from my paper. I already did these calculations. So 1 divided by the total or effective resistance in that area that we're looking at, where you have your resistors in a parallel format. 1 divided by 5.0 ohms plus 1 divided by no, that's not the numbers. I was copying from number 8. Let me erase these. Okay. I'm glad I noticed. 0.11 ohms, 0.78 ohms, and the last one, 1 divided by 1.2 ohms. So put everything in your calculator, and you get 11.2, 1 divided by ohms. So you're not done. Divide 1 by this number, and you find that your effective resistance for that area is 0.0892 ohms. Okay. Are we done? No, because we need to calculate to know what kind of fuse we need. We need to know what current we have. Once we know the current, we know what fuse we need to put there to protect us from the current. So let's calculate that current. How do we calculate the current? The current is your voltage divided by your resistance. Are we done calculating the resistance? No, we just had, let me see where it is. We just have found this resistance right here for this area, okay? You still have this resistance right here. So the next step is for you, to add them up, add these right here to find the resistance for the whole circuit. We need to do that. Okay, let's find that resistance. Let me go back to white. So the resistance total for these, or effective for this circuit, is the addition of those two resistance. Let me get my page so I can copy to see what number was there. Okay. The resistance here is 0.84 plus the number I just found. And the number I just found is 0.08. My numbers are coming up. We're 92 ohms. Add them up, and you should get a resistance of 0.93 ohms. Now I have everything I need to put it in my formula right here. That's 9.0 volts that was given to me, and I found the resistance to be 0.93 ohms. Okay, the amps is going to be my answer right here, and that's 9.7. So I know that whatever fuse I choose needs to protect me from current that is a little bit over this, okay, at least this amount. And you had options, okay? They gave you 1, 5, and 10. But to be able to protect you from this current, you needed to choose the 10 amp fuse, okay? Because 1 was not enough and 5 was not enough, so you need to go with the 10. There you go. We're almost done. So here you go. Next, I don't know why I keep going there. So the answer for number 10. Let me look at this. What did they ask for? They asked for the power. And the power that you needed to find was 3.8 watts. Okay, watts. If you found this, you are done. You're done with module 15. But if you did not get module, if you didn't get this for extra practice problem number 10, then watch to see how this is solved. Whoa, that's a whooper. Let's look at this drawing. You have lots of areas here. So let me draw this so we can break it down. There you go, resistor. Then you had some kind of like this. Just bear with me while we draw this. Another one of this kind here, and another one right here. And then the battery was placed right here. And can I move that? Let me see if I can move that. I don't know why this is here like that. Okay, I'm moving it up. Okay, there you go. And then you had two more. Lucky you. So here you go. This is connected here. And then you had two more of those. One here. Another one here. And yours can look prettier than mine. It's very hard to write with this pen. And another one right here. And that is your circuit. Well, you need to break this into areas. Just do that, okay? Let me get my highlighter. I hope everybody realizes that you need to calculate the resistance for this area. You need to calculate the resistance for this area. You need to calculate the resistance for this area. And you need to calculate the resistance for this area and try to make this more simple. Let's see what happens if we do that. Okay, draw. If you go like this, then this becomes one right here, and this becomes one right here, and then you have another one right here, and then you have another one right here, and then you have another one right here, and the battery is here in the middle. Whoa, okay. Well, so this is what it looks like right this minute. Let's do that, because then what I can do is calculate each section again. I'm going to start with those 4 sections, make it as simple as that, and then continue simplifying it. That's what I would do, okay? So I'm going to try to simplify this later. But I'm going to start with those 4. And I'm going to get my numbers in front of me so I don't make mistakes. Maybe I should name those. Let me name them. We don't get confused. This is going to be area 1, area 2. Did I name them like this? Yeah. Area 3, because I have it on my pages like this, and area 4. I'm going to solve each one of the areas. Okay, let me get my page out in front of me. It's a lovely problem, isn't it? It has a lot of different areas. Page. Let's try to solve area number 1. So area number 1. Everybody needs to realize that this is in parallel. So I'm just going to go ahead and put the numbers in. I'm going to calculate the resistance for that area. And from here, I'll find that my resistance, okay, is going to be 7.04 ohms. Okay. And you do that for every single area. Area number 2, you do the same thing. It's 1 divided by 68. It's 1 divided by 72. And I find my resistance to be 30 4 ohm. Area 3. Okay. 1 divided by R equals 1 divided by 22 ohms plus 1 divided by 15 ohms. And if you go all the way, you get your resistance to be 8.92 ohms. Next page. Area number 4. Area 4, I'm going to put it here, 2 dots, equals 1 divided by 54 plus 1 divided by 81. So if you do all the math all the way to the end, you find a resistance is going to be 32 for that area. Let me write down, let me do the drawing of what we found, okay? This is what we have right this minute. Ting, 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 another area of resistance, another one right here, and finally one here. So we have 34 ohms, 42 ohms, 7.04 ohms, 8.93 ohms, and then we have the 31 ohms. So we have simplified somehow, but we are not done yet simplifying. I have created 2 more areas. Okay, I have this area at the top, and I have created another area at the bottom. Did I not put the 32 here? And put the 32. This was 32. Well, I tried to write it, but the pen stopped working. Okay. So I have created 2 areas, and I know how to calculate the resistance for each one of them, because in these areas, you have the resistance in a circuit. So for this area, your resistance is going to be the addition of all these resistance, okay? So for the top, you're going to add them up, 7.04 plus 42 plus 34. If you do that, for the top, I'm going to put the top, the resistance for the top part of these, if you add them up, it's going to be 72 ohms. If I do the same thing for the bottom, so my resistance here at the bottom, I'm going to put just a B for bottom, you also need to be adding them up because they're in a series. So 8.93 plus 32 plus 31, if you add them up, I gave you the numbers incorrectly. The 72 goes here, 72 ohms. Let me erase. I want the eraser, this one. Let me make sure. The top is 83 when I add it up. Okay. So 83. The top is 83. 83. Okay. So if you add 34, 42, and 7.04, you should get 83 ohms. And if you add 8.93, 32, and 31, you should be getting 72 ohms. So what have you accomplished by doing this? What have you accomplished? You are simplifying this circuit. What do you have now? You have this. Okay. So you see, they are tedious because there's a lot of simplification, but the math is not that difficult. You found that this was 83 ohms and the bottom was 72 ohms. And the voltage was given to you, it's 12.0 volts. Okay. How are they connected? These are in parallel, okay? I hope you notice that this is a parallel circuit. So you can now finish finding the resistance, because if you want to calculate your power, you know that you need your current times your voltage, and you are missing your current. So to find that current, you know you needed to have your voltage divided by your resistance for the whole circuit. That's why we have been calculating that resistance. So let's do that. Let's find the final resistance for this circuit. And because they were in parallel, we're going to be using this formula, okay? So 1 divided by 83 ohms plus 1 divided by 72 ohms, and that is 0.026, 1 divided by ohms. And that makes the resistance total for the whole circuit to be 38 ohms. Now we can use our resistance to find our current. And that is a 12.0 volts that they gave us, that was given to us, divided by the 38 ohms that we found ourselves. And if you do that, your current is 0.32 amps. Not done yet though. Almost done. Almost. Now we can calculate that power. So power equals current times our voltage. The current is 0.32 amps multiplying the 12.0 volts. And if you put all in your calculator, you find that that circuit has a power, electrical power of 3.8 watts. And now we're done. And that was the last. So remember, they look complicated, they look crazy, okay? But break it into areas, simplify, and then simplify again. Keep simplifying, top and bottom. Decide, are they in parallel? Are they in a series? And then use the correct formulas to continue finding what you need. I hope everybody is keeping safe. I'll see you at Zoom if you need me for anything, or you can email me and ask me questions. Keep safe. Thank you.